and this first film is about the properties of light. We are later going to look into optical sources, transmission media, and optical detectors. First of all, the electromagnetic spectrum ranges from long waves, radio waves, TV waves, microwaves like the ones you find in your microwave oven, infrared, and visible and ultraviolet. So this is the part of the spectrum that we talk about in this lecture here. And then at shorter wavelengths or higher frequencies, you have X-rays and then finally gamma rays. But again, this part of today's lecture is about infrared, visible and ultraviolet light. The physics of light. Snell's law, named after Willibald Snellius, states that there is a relation between the light that you send in and the light that is transferred to another media. When you send the light to another media, the light will bend according to the so-called refractive indexes. So every material comes with a refractive index, at least the transparent materials, and there is also a relation between the velocities. So in this case, we have a higher refractive index here in this blue media compared to the white media here. And hence, because of the higher N2 compared to N1, the angle changes as well. So therefore, theta 1 is larger than theta 2. And also the velocity V1 is larger than the velocity V2 in this case. Also remember that the speed of light in vacuum is about 3 times 10 to the 8 meters per second. And the velocity will therefore, if you have a higher refractive index here, the velocity will go down. So there is no material with a lower refractive index than vacuum, because there is nothing that carries light faster than vacuum. So here are examples of some refractive indexes. You have vacuum defined as 1, air very close to 1, so for most practical cases we can think that the refractive index of air is the same as the one in vacuum. Ice 1.13, water 1.33, they are all higher. When we come to glass, it's between 1.5, 1.6. And we have here flint glass, for example, and the highest we have in which naturally occurs is diamond. So with a refractive index of 2.42. Refractive index or total internal reflection. When we have a light that goes from a source in a high refractive index over to another material with a lower refractive index, the beam will bend away from the normal. The normal here is shown in a red dotted line. So the beam will bend away from it. When the angle increases, you come to something called the critical angle, theta c, where the refracted wave, the refracted beam, falls on the interface between the two materials. If you increase the angle furthermore, you get what is called total internal reflection. That is when all the light reflects to the other side. Note that for the other angles here, some light will reflect and some will refract. Some will go into the new material. In this case, the more the angle is, the more reflection and less refraction. But when you come above the critical angle, everything will reflect. So this will, for an angle higher than the critical angle, this will become a perfect mirror. And I think this picture is quite funny. It's from the old record album Nirvana, Nevermind, which you should really listen to. It's a beautiful record. But the picture here is taken from a high refractive index up to air, which has a lower refractive index. And you see the water or the interface between water and air becomes a perfect mirror. This is actually the same guy a few years later, and you see the interface between air and down into the water, and you see that when you go at the higher angle here, you will always see something through over to the through the water air interface. So this will not give total internal reflection, while you will get it here in the interface between water and air. So when you send light from high refractive index to low, you will get total internal reflection, given that the angle is high enough. But when you send light from low to high, you cannot achieve total internal reflection. You will get some reflection, but not total internal reflection.